Let's start talking about application security, threats, and attacks. This is Module 1 of the CASE.NET course. In this module, we're going to try to understand and explain to you carefully the various attacks that your application is likely to be subjected to. Put another way, the best way to learn secure programming is to first learn what it is you're securing your application against. So our objectives here are to understand the benefits and needs for application security, discuss the most common application level attacks, discuss the reasons those attacks exist, in other words, what vulnerabilities lead to those attacks being possible, discuss the various components of comprehensive application security. What I mean by that is we don't want to just secure little pieces, we want the entire application to be secure. We will also understand the need and advantages of integrating security throughout the software development lifecycle. Security shouldn't be something we tack on at the end, but rather something we do throughout the entire process. We'll differentiate the functional activities versus the security activities in that software development lifecycle. We'll discuss Microsoft's security development lifecycle. Since we are focusing on .NET, looking at Microsoft's model is very beneficial to us. And we'll discuss a variety of standards, models, and frameworks that may be helpful to you in understanding application security. What is a secure application? Well, this ties back to the old adage in security of confidentiality, integrity, and availability, what's commonly known as the CIA triangle. Those three concepts are the bedrock of all security, including application security. So again, what is application security? What is a secure application? It's an application that maintains confidentiality, maintains data integrity, while still ensuring data availability to the intended users. So we want to restrict any access to only those authorized users. And as you'll see throughout this course, users is not limited to human users. What about other systems that might be accessing the data? That's very common in today's complex applications. Organizations are increasingly using web applications. You can do virtually anything through a web application today. Make travel arrangements, arrange for banking, take online courses, whatever you might desire. For that reason, web application security is becoming ever more important. I am certain that in recent times you've seen some news story involving some major web application breach, some website that was intruded upon by attackers. Well, web application security seeks to prevent a great deal of that. What happens when a website is breached? Can be financial loss. It can be the loss of personal information. It can be embarrassment to people's confidential data. It can in fact lead to closure of businesses entirely, particularly for businesses that are dependent all or mostly on e-commerce. A major breach can end that business. It can certainly damage a business's reputation. So there are many reasons we want to avoid our web applications being vulnerable to these issues. There's a quote from Carlos Lyons. He's from corporate security at Microsoft, and this quote's very important. A vulnerability in an application will allow a malicious user to exploit a network or a host. So what we're talking about are any weaknesses in an application that might allow someone to attack it. Now, it's a common myth that if we have enough security controls in our perimeter, things like intrusion detection systems, firewalls, perhaps even honeypots and web application firewalls, the myth holds that if we have enough of that, then our application is secure. And that's just not true. First of all, by definition, your web application has to be accessible. Ports 80 and 443 are commonly open for web traffic. Well, if those are open, then they're not being blocked by the firewall. Traffic through those ports is unlikely to trigger an intrusion detection system. And users are accessing your web application, they're unlikely to be tricked into a honeypot. For those reasons, those devices are not enough. Now, don't get me wrong, I'm not saying you shouldn't have those devices. Those devices are part of your network security, but they're not going to provide you with application security. Secure coding practices will do that. Another quote, this comes from the Gartner report. If you've never viewed that report, it comes out every year and provides a lot of insight into various security issues. But here's a quote from the most recent report. Nearly 75% of all attacks on information security are directed to the web application layer. Now that number is probably going to fluctuate over the years, some years being more, some being less, but that's a profoundly surprising number, 75%. So if we're not securing our web applications, frankly, the rest of our security measures are really ineffective. Another quote from that same report, 2/3 of all web applications are vulnerable. Let that sink in for a moment. We know that 75% or 3/4 of attacks happen via a web application, and now we know that 2/3 of all web applications are vulnerable to some attack. It really is a surprise that we don't read about more attacks in the news. So let's look at some common attacks. It's a really good idea to understand how these attacks are done, how they're executed, so that you're better able to defend against them. SQL injection. Now this type of attack has been around for a very, very long time. In fact, we'll talk later about the Open Web Application Security Project, OWASP, and injection attacks have been on their top 10 list for well over a decade. That means they're not obscure, but they're still happening today. SQL injection attacks essentially amount to an attacker looking for some aspect of your website that allows them to enter text, perhaps a username and password, and rather than just entering what they were supposed to, they enter some strange-looking text that's designed to trick the SQL command into processing this in a different way. Put another way, SQL injection is all about the attacker understanding structured query language and manipulating it to get around your application and get past your authentication and authorization methods. Now, one thing that's very important to realize, virtually everyone in security is at least moderately familiar with SQL injection, and we show a very basic form on the slides here. However, SQL injection can go much, much further than this. In fact, once someone can successfully enter your application using SQL injection, at that point they're really only limited by their knowledge of SQL, their knowledge of databases in general, and their patience. There are a lot of very terrible things someone can do with SQL injection. Cross-site scripting is another attack that can be very devastating. Essentially, cross-site scripting depends on the attacker finding some spot in your website wherein users are meant to enter text that will be displayed to other users, perhaps product reviews. And instead of entering that text that you intended them to enter, like a product review, they put in some sort of script, often JavaScript. Now, JavaScript, if you haven't worked with it much, is a very easy scripting language to learn, but it's also very powerful. There's lots of things I can do if your site is susceptible to cross-site scripting. I could redirect users to an alternate site. That alternate site could be a phishing site that harvests their username and password, account numbers, things of that nature. I could exploit user privileges. I could manipulate data. I could take over their session and then behave as if I were them and do whatever they would be authorized to do. It can be used for password cracking. It can be used for key logging and remote monitoring. One of my favorite exploits with cross-site scripting is to use the JavaScript, if that's the scripting language they're using, to read back all of your history. In other words, if you've been surfing the internet, say for an hour, and you then visit a website that's susceptible to cross-site scripting, and it's been infected with a cross-site script. Well, what I could do with that script is look at all you've done up to that point, all the other websites you've visited, and possibly even the data you've submitted to those websites. Now let that sink in for a moment. This means potentially cross-site scripting, if done effectively, could not just exploit users to this website, but could render other websites you visited susceptible to some data exploitation, even without exploiting those websites themselves. This is a pretty serious problem. And it really starts with the same place SQL injection does, not validating user input. Now, this is something you're going to hear throughout this module and other modules. Never, ever trust user input. You always validate it. And we'll tell you how to do that throughout this course. Now, in the slides here, we show you an example of a particular cross-site scripting attack. In this case, the script was actually uploaded in a particular file. The user visits a website expecting to see some content from other users, but instead the script is executed and it can do anything I want them to do. Redirect them to some other site. What you're seeing here is redirecting someone to a fake login site. That way they type in their username and password. Then I send them back to the real site. Now, from the user's perspective, they were on a website that requested them to re-enter their username and password. No big deal. But what's really happened is I now have their username and password and can log into the site as them. Parameter tampering. It's becoming less common, I'm glad to say, but for the longest time, web programmers would take various pieces of data that they need to pass from one part of the web application to another, and they'd put them in the URL as parameters. Well, if you're doing that, it's certainly possible for an attacker to manipulate those parameters. One of the things you see here on the screen is changing a debit amount from $2,500 to $1,500. Well, that's devastating in and of itself. But the second example is even worse. Instead of viewing something, we're deleting something. In other words, the attacker is using parameters to delete content from your web application. These are just a few of the things that can happen with parameter tampering. Directory traversal. If your web application is securely programmed and your web server is securely configured, the user visiting your website, whether that's a legitimate user or an attacker, is limited to the folders and directories you've provided them. However, if things are not configured properly, it is possible to manipulate variables and move back and forth into other directories. You can see on the screen here there's a combination of dots and slashes designed to give me access to some other part of your server. Now think about this for a moment. You have a web server. Perhaps it's running Microsoft Windows Server 2016 and IIS. You'd like to have the person limited to the www root directory. But if I can use directory traversal and get outside of that directory, I can do any number of things. For example, I could possibly copy the SAM file and get that server's passwords and later subject them to rainbow table attacks and eventually have your administrative passwords. That's just one example. The concept here to understand is that directory traversal, it requires a little patience, and not all attackers will try it, but if your web application and your web server are susceptible to it, the effects can be quite devastating. Cross-site request forgery. One of the best ways to describe this is it's the flip side of cross-site scripting. Cross-site scripting attacks the user based on the fact that the user trusts the website and isn't aware that the website's been compromised. Well, cross-site request forgery flips that around. In this attack, we're going to attack the website based on the fact that it trusts the user. And the name pretty much suggests what's happening. You find a user that's authenticated, they have an active session going on, and the attacker forges HTTP requests that appear to come from that user. Now, given that this user's been authenticated and vetted, the website is more likely to trust those requests and less likely to go through additional validation and verification steps. Now, of course, we're going to teach you to go ahead and do those extra steps so that you're not susceptible. But if a site is susceptible, a lot of bad things can be done by the attacker because the website's trusting these HTTP requests and commands. Now on this screen, we're seeing an example of how this might work. We have client-side code that's used in this case to purchase something. And we're executing malicious code on the trusted server by sending it as a request that's forged from the trusted user. This is a good example of cross-site request forgery and how damaging it can be. Denial of service attacks. There are so many variations of denial of service, but they all seek to accomplish the same goal: to in some fashion overload some service so that it can no longer respond to legitimate users. In other words, I have given the server or the application so much work to do, it can't now respond to the legitimate users that need it to do something. There are all kinds of targets here. For applications, it can often be simple database bandwidth or spawning off extra threads or anything that causes the service to exhaust its resources and be no longer able to respond to end users. Now we see a few examples here. User registration. You get a program that constantly submits new user registrations. And by constantly, this could be thousands in a few seconds. Well, the system needs time to respond to all those new user registrations and now can no longer process real users. User enumeration, simply going through trying common usernames from a dictionary file. Now you might think this is unlikely to get me to log into the system, and you'd be right. The goal here is not to circumvent authentication, it's to overwhelm the system. The system's trying to validate and authenticate all these login attempts, and even though they fail, even if you have a lockout, then I'll simply start with another username. And again, this is automated usually through some script to overload the target system. Login attacks. The attacker can simply overload the login by continually sending login requests, and I may even do that without even going to the web form, just sending HTTP requests directly. Another one that you don't see that often but can be devastating is deliberately locking out legit users. Let's say I know your username configuration. It's first letter of the first name and then last name. So I'm going to attempt to log in as J. Smith. I'll do it 3 or 4 times until you lock out. And then I'm going to try M. Smith and N. Smith. My purpose here is to lock out all your legitimate users, so when they try to log in, they're going to have to find a way to get their password reset, which is going to disrupt your services. Again, that's not such a common attack, but it's perhaps the easiest to do. Think about it for just a moment. This attack does not depend on successfully breaching your security. In fact, I'm expecting that your security is so good that you're going to stop me. All I want to do is lock out the accounts. And particularly for very secure sites where those might be lockouts that automatically extend for days or require the user to call in to an administrator to get a reset, things of that nature, an account lockout attack can cause a lot of disruption. Cookie poisoning. There's nothing wrong with using cookies. In fact, cookies are a common fact of web applications. You've probably visited websites that informed you that they needed cookies to operate. And it'd be very difficult to do complex applications with no cookies. But if you don't handle them securely, there are a number of ways to attack the cookie. One of the simplest ones is, if the cookie is done poorly, it may simply indicate that a user is authenticated with a date timestamp. Well, if I detect that, I might change the date timestamp so you think I'm an authenticated user well after that user has timed out. That's one example. It's not easy to do, but it can be done. Other examples include modifying the cookie content, injecting my own content, adding my own information, or rewriting the session data altogether. Now, modifying the cookie content is probably one of the most common, because one of the issues the attacker has to address is if he's going to put data in there, it must be in a format that your application will recognize. So if I'm modifying existing content, I can see exactly the format you use and simply alter it. Injecting the malicious content, there's a chance that I won't put it in the right format and it won't be processed. Here we see an example. We've got an option here to checkout, and the cookie has a price in it. That price is $11,568 or euros or whatever currency you prefer. Well, I simply change that so it's $100 or $10 or whatever amount I want. Now again, cookies can be used. They probably shouldn't be used for pricing data, and they should be used in a secure fashion. And we're going to show you how to do that throughout these lessons. Session fixation. Here's the bottom line. Normally, web applications have a user authenticate and provide them a session, and that session will time out after some time. So what happens here is the attacker sends an email containing a link with a fixed session ID. If a user clicks on it, they're redirected to some website. Now, in our example, we're using a bank website because those would be obvious places for an attacker to want to breach. The user logs in using their credentials and the fixed session ID. Now the attacker can subsequently use that same session ID. Now there are ways to handle session IDs that we're going to explore that make this attack impractical. Okay, we've looked at a few common attacks, and these are not all the attacks out there, but they're the most common you're going to see, and cross-site scripting and SQL injection may be the most common of these. But this leads us to a question. Why are applications vulnerable to these attacks? I told you at the beginning of this module that these are well-known attacks. They're not obscure. So why are they still out there? Why are there still such vulnerabilities? Well, there's a few reasons. First of all, a lot of the software that's out today was never even contemplating security. Let me put that another way. If you go to most colleges and you take a computer science or CIS or computer engineering degree, in many cases it's possible to go through the entire degree and never have a single course that addresses secure programming. Now, depending on the specific track you go, you may take advanced courses in algorithm design. You'll certainly learn various programming languages. You may even get into operating system design and all sorts of really interesting classes. But you literally could get a degree from most universities and never have encountered secure programming concepts. Another problem is the stakeholders aren't always aware of how important this is, so they try to tack on security at the end instead of throughout the development lifecycle. Another problem is failure to gather application security requirements. We have a whole module dedicated to this because it's so important. As you'll see later in this course, the earlier you address security, the easier and cheaper it is to do it. So starting at the requirement stage should be an obvious place for us to begin. Improper application of the security principles during design phase. Once you've moved past requirements and you're into design, it's important that we implement security in that design appropriately. Now, unfortunately, so often we're focused on the features that users want in our application, whether it be interesting graphics or certain functionality, and yes, those things have to be there, but we must focus equally on security in design. Insecure coding techniques. Now, this goes back to the fact that many programmers have never learned what the secure coding techniques are. So they're unlikely to be able to implement what they don't know. We're going to correct that in this course. Lack of security testing. Now, I'm sure most of you have done lots of software testing, and you're normally testing for the functionality that your application was supposed to provide. If you're writing an application for an airline, then your web application has to be able to process tickets and book flights and select seats and things of that nature. And that's probably what you test for. And you should. I'm not saying you shouldn't. But we must add to that robust security testing. And finally, security negligence in the deployment phase. Your web application is going to be deployed on a web server. Is that done in a secure manner? And we'll look into that during this course as well. Some of the flaws we see due to insecure coding. The first one, and this leads directly to SQL injection and cross-site scripting, is improper input validation. I can't say this strongly enough. If proper input validation was implemented throughout all web applications, we would never again hear of cross-site scripting or SQL injection. But people don't know how to properly validate input. Insecure cryptographic storage. There are really great, robust encryption algorithms out there that are not likely to be cracked by anyone in any near future. However, if they're not implemented properly, there's a problem. For example, let's say you use AES 256-bit to encrypt confidential data on a hard drive. Well, that's a wonderful choice, unlikely to be broken even by government entities. However, you use a very ridiculous password for it of password. Well, I don't have to break AES to get at your data. I just have to guess your really bad password. That's an example of insecure cryptographic storage. Insufficient transport layer protection. Your data moves back and forth across the internet. And if you're not already aware of this, There are a variety of attacks that can be executed on SSL or now TLS to attack that transport layer security. If you've properly implemented your transport layer protection, those attacks won't be successful. Insecure direct object references. Programs are very complex today, and there's a good chance that you're referencing a lot of external objects. We need to make sure that's done securely. Broken authentication and session management. You saw a trivial example earlier in this module where session IDs were stored in a parameter. Well, that's a very bad way to do session management, and that's going to be exploited. We're going to teach you in this course how to do that much more securely. Improper error handling. It's very common for people to not have adequate, sufficient, or appropriate error handling. It's not enough just to catch an error and log it. You have to do specific things depending on the nature of the error. Unvalidated redirects and forwards. I mentioned one of the things I can do with cross-site scripting is to redirect users to a phishing site. Well, that occurs because your web server and web application are allowing unvalidated redirects. If you can prevent that, then I can't redirect them anywhere else. Failure to restrict URL access. That's all about preventing parameter tampering and preventing directory traversal. If you can do appropriate URL access restriction, you can prevent those two attacks. Now let's talk a little bit more about improper input validation. The bottom line is any data that's being put into your application must be processed and validated. And we're going to look at a lot of specific techniques. If you don't validate it properly, there's a number of injection attacks, SQL injection being just one. Or they may simply put in bogus data, but there's a whole lot of attacks that get prevented through proper input validation. Insufficient transport layer protection. It could allow third parties to simply read the data. It wasn't encrypted properly. And I've unfortunately seen a lot of scenarios where only data in certain situations is encrypted, other data is being sent in the clear. And that means anyone with a packet sniffer can get your data. Underprivileged SSL setup can let someone launch man-in-the-middle attacks. There are a variety of ways to set up SSL, or now TLS, of course, that are very secure, but if you do it improperly, someone can execute a man-in-the-middle attack, in which case they're between the two endpoints and seeing all the data. Using expired or invalid certificates. I don't know how often I have seen websites that are using either old certificates or self-signed certificates that can't be validated, or certificates that are not only self-signed, but use outdated, weakened algorithms. We're going to talk a lot about encryption and its role in secure application programming later in this course, but for example, RSA keys should be a minimum of 2048-bit today, and 4096 would be a much better solution. If you're using an old certificate with, say, a 1024-bit RSA key, there's a lot of vulnerability to your transport layer right there. Improper error handling. Well, first of all, don't give the external person too much detail. We'll see this in much more detail later, but oftentimes people just bubble up to the end user whatever the underlying raw error message is. Well, attackers can use that to learn about underlying systems, what database you have on the back end, what coding techniques you used, all kinds of things about your network, and just a whole host of information that makes their attack easier. Beyond that, these messages are usually just confusing and frustrating to the end user. It's a better idea to simply tell the end user, there's been an error, if need be, contact technical support. Don't give them all of these details. And you can see on the screen here, this is an SQL error that gives a huge amount of information about the underlying database. For an attacker, this is beautiful. I can see exactly the SQL statement you were attempting to run. I now know table names and column names. Wow, if I were a bad actor seeing this information, I would be absolutely ecstatic because I now know more about your database than I would have hoped to have learned. Insecure cryptographic storage. The algorithms we have available today and that we've had for many years are quite secure. Blowfish, AES, Serpent, RSA, elliptic curve. These are all pretty good algorithms, at least with modern computers. Quantum computing may change some of that, but at least for now, these are good algorithms if they're implemented appropriately. If you reuse keys, improper key storage, bad passwords, things of that nature will allow attackers to steal or modify your data. Broken authentication. We mentioned before session IDs in the URL. I'm happy to say that's becoming less and less common, but it shouldn't occur at all. What about gaining access to the password database? If the passwords are not stored as hashes as they should be, using cryptographic hashes, the attacker sees all the passwords. That's one common example of how someone could use bad session management and authentication. What about timeouts? First of all, the timeout should be very short. If there's a period of inactivity that goes any significant length of time, the session should time out. There's been a real problem with hotels on this issue. People log into an application, maybe it's a banking application, and they forget to log out when they get up from a hotel computer that's in a common area. Well, if that application doesn't time out quickly, the next person that sits there can get into your bank. Well, that's a pretty disconcerting scenario. Unvalidated redirects. I send an email that has perhaps a rewrite link to some server, and I redirect the user to my attack server. I forward users to some attack website on my attack server. These are just a few examples of how I can trick a victim into visiting another website. Now, what do I do on my other website? Anything I want to. Install malware on the user's machine, steal their login credentials. I'm only limited by my own creativity and my own malicious intent. So unvalidated redirects and forwards are a very serious problem, and we'll be addressing those in this course. Insecure direct object references. When you're referencing an object, and that could be a file, could be a directory on the server, a database record, anything of that nature, it's important that we do this in a secure manner, or else the attacker can use those references to gather information. For example, information about database records or directory structure. Failure to restrict URL access. There are certain pages in your application that have sensitive information. Now, this is one I've actually seen, and unfortunately, on quite a few ASP.NET applications, and I've seen it recently. I go to a website, and there's a login page. I don't have the login, but I'm guessing that one of the pages might be called account.aspx, so I just type that in at the end. I have seen applications that allow me to circumvent the login and go straight to that account page. Now, that would be a very, very insecure website and probably one of the most egregious examples of failure to restrict URL access, but it illustrates the point. It allows the attacker to use what's called forceful browsing to force the web application to go directly to the page they want to go to, as opposed to the ones they would visit through normal use of the web application. What constitutes comprehensive application security? Now, before we delve into that, I want you to focus your attention on that word comprehensive. It's not sufficient to do a few pieces here and there. Unless you have comprehensive application security, you don't really have application security. And allow me to put this in a way that I think will make sense to you. You, as the secure programmer, have to be right every time. The bad guy only has to be right once. So if you don't have comprehensive security, you may have 2 or 3 things that you've addressed excellently, and your security is profoundly good. But that one thing you missed is all the bad guy needs. Here's another quote, and this comes from the aforementioned Open Web Application Security Project. Software applications are designed and developed with functionality first in mind, and security is a distant second or third. Now, they're not stating this is how it should be. They're saying, unfortunately, this is how it frequently is. This diagram here shows you a general overview of an application security framework. And you can see there's a number of elements, including auditing and logging, cryptography, input validation, authentication, configuration management. All of these are part of the application security framework, but they also work hand in glove with securing the actual server, the host, making sure it's patched, making sure it has good account management, using secure protocols, auditing and logging. And that goes hand in hand with securing the network. So we still need those firewalls and intrusion detection, intrusion prevention systems, good router and switch security. We need all of those to work together with our application security. Now, we started this off by saying that using various technologies like IDS and firewalls isn't enough, but secure coding alone is not enough. Coding securely alone does not guarantee or ensure secure software development. Some missed requirement, in other words, you didn't do good security requirements gathering, or a bad design, or a bad architecture can still make your application vulnerable to a number of different attacks. There are 3 W's that you need to keep in mind throughout this course and on in your actual development time. These 3 W's are why, what, and who. Why do we care about application security? Well, again, because web applications are becoming so popular and they're by nature globally accessible, they're becoming seriously attacked on a regular basis. What do we need for application security? Well, one of the things we'll talk about is a philosophical approach that is constant security vigilance at every phase of the software development lifecycle. Who's responsible for application security? Well, yes, management is. Yes, architects are. Developers, testers, administrators, everyone involved in the software development lifecycle is responsible. Insecure applications, these are a real problem with software development. We're looking here at the software development lifecycle. We have requirements, design, development, testing, deployment, and maintenance. Now you'll notice what we've put in this graphic are security items to address at each of these stages. So let's start in requirements. You have to gather security requirements. Now that may sound a little vague. We'll get more specific later, but as an example, what level of encryption do you need? How frequently should users be required to change their password? These are security requirements. Design. Security requirements go into here, and then we are also adding secure coding standards. For example, if you're processing credit cards, there are specific PCI requirements you need to keep in mind. If you're doing Defense Department coding, the NSA sponsors a whole list of security requirements. We're going to talk a lot in this course about threat modeling, identifying the specific threats you're trying to defend against. It's not enough to say, I'm going to defend against everything. You have to know who your attackers are. As an example, I was asked earlier this year by someone if they should be concerned about foreign nation-state hackers attacking their network. Well, I naturally asked the person, what kind of network do they administer? And they told me they were the network administrator for a small high school. Well, no, their threat model does not include nation-state hackers, but it does include very rambunctious teenagers who've watched all the hacking movies and downloaded tools off the internet and will definitely be trying SQL injection. That's a crude example of threat modeling, understanding who your threats are and who they aren't. And of course, we'll be talking about development. The secure coding standards feed right into here, and then we'll look into frameworks and secure coding practices. Testing involves many things. Of course, it involves code review, looking through the code to make sure you facilitated and implemented those secure coding standards. Then vulnerability scanning. There are a lot of great tools for this, some of which are even free, which will aid you in this process. And actual pen testing. Now, this is just a personal opinion, but I believe that any situation, whether it be your network or your application, if you've not had a competent pen tester penetration test your application or your network or your server or whatever it is you're concerned about, then no matter what else you've done, you're guessing you're secure. You don't really know. Until someone who knows what they're doing truly attempts to breach your security, you really don't know. Now, a lot of people do think about security at testing. In fact, that's usually when most people start thinking about it, but we go beyond that. secure deployment, and secure maintenance. Maintenance, patch management comes to mind. I was actually teaching a security class when WannaCry hit, and I discovered quickly how many of my students were actually surfing the web because they all became quite excited as they saw this breach spread throughout the world in the space of an hour or two class. Thousands upon thousands of machines were hit. Now, why is this relevant to maintenance? Because there was a patch available at least 6 weeks before that would have made all of those systems invulnerable to the WannaCry attack. That's just one example of many where just not doing secure maintenance is a problem. Functional versus security activities. The functional activities are making sure, essentially, that your application does what it was meant to do. If it's a banking application, can it process payments, deposits, debits, set up bill pay, things of that nature, wire transfers? This comes down to your functional logic. You do unit testing to make sure it can do these things, and you ensure that you update that functionality as needed. Now, security activities are similar, but there are some differences. For example, we're much more concerned with threat modeling and architecture here. We're going to need to use white box testing as well as black box testing, even more so here. We're going to make sure we have security patches, not just for our application, but for the underlying operating system and web server. These are a few of the differences we're going to be explaining and exploring during this course. What is the advantage to integrating security so early? Put another way, why not do what we've always done and just wait to the testing phase, try to tack on security at the end? Well, the bottom line is it's much easier to address anything early in the process than later. Imagine you're building a house and you wait until the house is completely built to decide you'd like to extend the dining room 5 more feet. Well, you're going to find that's tens of thousands of dollars to remodel. If you'd made that decision during the architecture phase, it might have been almost free. The same thing's true of your software. So by doing security throughout the software development lifecycle, we're going to reduce software vulnerabilities a tremendous amount. We're going to comply with any regulations or standards that are necessary, and there are more and more of these standards coming. If you do any business with Europe, GDPR has got to be a concern for you, and that's going to definitely impact your application development. We already mentioned PCI and NSA standards, and there are a number of others. Reduce costly rework. If you wait till testing and you discover a significant vulnerability, well, now you've got to rewrite code, and then you've got to retest that rewritten code. This costs time and money. Developers get a lot more satisfaction. Developers, in my experience, are creative people. They like to develop new things. They don't like going back and fixing stuff that should have been done right the first time. That's not interesting or intriguing work. So you're going to improve the developer's job satisfaction. Customers are going to be more satisfied because not only do you provide them a more secure product, but it's more likely to be on time because you were addressing security from the word go, not waiting till the end. This is going to embed a security culture. And again, one of my own personal opinions is that security culture may be the most important part of security. If people are thinking about security all the time, that's going to mean more than any particular standard or technique could possibly mean. If you understand security from the beginning, and all of your modules are securely developed from the beginning, then it's easy to reuse those in other projects. And this will significantly reduce your maintenance cost. Now, we've talked about the standard software development lifecycle that I'm sure you're all familiar with. Let's take a brief look at Microsoft's security development lifecycle. This was developed by Microsoft with the explicit purpose of training people and getting them to develop secure applications. There are 7 phases, and I've got to tell you, I absolutely love this first phase, training. This is before we've even done requirements gathering. They're suggesting that you get the developers and related people such as administrators, managers, testers, people like that, trained in security. Courses like the one you're viewing right now are part of this process. So before we even start talking about requirements gathering, let's do training. Now then you can see the requirements in design, which are pretty much analogous to those you see in the system development lifecycle model. Implementation is when we actually do our coding. We need to make sure we're using good coding tools. Avoid any unsafe functions. Now, what do I mean here? As programmers, we use code libraries all the time. You've probably used open source code, inserted it into your programs, or you've used external libraries. How certain are you that these external sources are secure? Let's make sure that they are. Using deprecated functions. Programmers do this all the time, and they need to try to avoid it. The functions were deprecated for a reason. Make sure you understand that unless there's no other way to accomplish your goal, move to the newer function. Then we move on to verification, and this is the testing part where we're doing dynamic analysis. We're doing fuzz testing. Now, if you're not familiar with it, we'll be discussing the testing later, but fuzz testing is essentially intentionally introducing data outside of bounds. For example, you want a user to enter their age. Well, what happens if they enter 0 or 235? What does your system do? Things of that nature. And looking at the entire attack surface. What are all the different ways an attacker could attack your application, and making sure you've tested those. The release. When you do the release, you need to immediately have an incident response plan in place. What are you going to do if, despite all of your secure development, all of your secure testing, some flaw does make it to production? Do you have an incident response plan in place? Do a final security review and archive the release version so you can roll back if need be. And finally, the response. Unfortunately, doing all the things we're talking about is not going to eliminate security threats and vulnerabilities. I wish it could. It is going to drastically reduce them. But there's still the possibility, even the probability, that some vulnerability will still make it into production and there'll be some attack. So the response is when you actually execute that incident response plan. Software security standards, models, and frameworks. Let's take a look at some of these before continuing. I've already mentioned to you before the Open Web Application Security Project. You can see their website here. They are pretty much the gold standard when it comes to web application security. They keep a running update of the most common vulnerabilities. In fact, about every 3 years, they publish their top 10 vulnerability list. They have tools that are free that will help you check for those vulnerabilities, and extensive documentation on how to go about doing secure web programming. Now, these are the top 10 attacks as of 2017. You notice number 1 is injection. Well, that was number 1 in 2013 and 2010 as well. That's a sad commentary on secure programming as a profession. We're not doing a good job. The others listed here: broken authentication and session management, cross-site scripting, broken access control, security misconfigurations, sensitive data exposure, insufficient attack protection, cross-site request forgery, using components with known vulnerabilities, and unprotected APIs or underprotected APIs, either one. Now, these are the 10 most commonly found vulnerabilities. It's important you understand this distinction. The OWASP top 10 list are things they actually see in the real world. These are the top 10 vulnerabilities they find in real websites. There are other sources we can look at. The Web Application Security Consortium. They're an international group of experts and practitioners that come together and establish some guidelines for web application security. They're not as well known as OWASP, but they're a very good source that you can review to get information on how to do secure programming. They have a threat classification system where they look, and you can see in the slide here, they look at specific attacks and what weaknesses those attacks are exploiting. For example, content spoofing. That's dependent on improper input handling. HTTP response smuggling. That is related to insufficient password recovery. Each of these attacks and weaknesses are related to each other, and it's easy to see how certain weaknesses lead to a wide range of attacks. Software Security Framework, the Security Assurance Maturity Model. Now, you're probably aware there are a wide range of capability maturity models that have been used throughout systems and software engineering. The Software Assurance Maturity Model is a framework to help organizations look at their software security maturity levels. It's designed to help any organization evaluate their existing software security practices and build a balanced security assurance program and demonstrate concrete improvements. Now, if you think about it for a moment, all maturity models are about demonstrating concrete improvements and giving you a pathway to continue improving. Finally, this particular maturity model helps organizations to define and measure security-related activities. That measurement aspect is very important. I've heard it said that what gets measured gets improved. In other words, if you don't measure things, it's unlikely you're going to make a serious improvement. So, for example, when it comes to security, are you measuring the number of bugs in perhaps a week worth of work? Are you measuring the number of malware outbreaks? Things of that nature. Now, here we see their module a little more detailed. They look at various ways to apply the maturity model. Look at governance. Now, this goes outside of the actual hands-on programming, but how is application security managed throughout the organization? Now, construction gets right into specifically how you actually write the code. Verification looks at the testing process, and deployment, how we go about doing software deployment. Each of these areas have to be addressed. Now, as programmers, we're most concerned with construction and verification, but all of the areas are important. Software Security Framework, this one is Building Security in Maturity Model. It's another maturity model, and it again looks at different areas. You'll see we have governance here, but we have a few other differences. Intelligence and what they call SSDL touchpoints. First, let's talk about intelligence. This goes back to threat modeling. Do we understand who our attackers are, how they're going to get into our system, and what countermeasures we have? Have we referred to specific standards and requirements that will guide us in this process? Our touch points. Have we analyzed our architecture? Have we done a good code review? Have we done adequate security testing? And then deployment includes penetration testing. Now you'll notice each of these models we look at has some overlap. For example, the governance portion here is very much identical to the governance portion we saw previously, but there are differences. And it's not the case that you have to adapt one of these to the exclusion of the others. In fact, I encourage you to look at all of these models, and for this one here, the two parts that I like most are the intelligence segment and the fact that pen testing is a part of deployment. I think that's something that virtually any organization can benefit from. So this framework has taken 12 practices and organized them into 4 domains, and you can integrate this into your own secure programming methodologies. And here we see a comparison of these two different maturity models. The one on the left, the BSIMM, is a descriptive model. The one on the right is a prescriptive model. In other words, one tells us how things are and the other tells us how things should be. They both have 12 security practices, but they've broken them down to a different number of activities. That really has more to do with the focus of the designers of that maturity model. And again, the BSIMM is descriptive, so it looks at the things that are actually being done. OpenSAM is prescriptive, and it looks at the things you should do. BSIMM has an active community that's involved in constantly updating the standard. There isn't one for OpenSAM. It's not that active. Now, to summarize what we've talked about, an application is said to be secure when we've implemented the entire CIA triangle of confidentiality, integrity, and availability, when we've restricted resources and secrets from malicious use. Attackers are exploiting various application vulnerabilities to steal secrets and gain unauthorized access. Just having the network security, the firewall, and the IDS is not enough. Applications are vulnerable to a range of different attacks that won't be addressed by those security measures. There are a lot of reasons for vulnerabilities, and we've covered those, and we want to address those throughout this course. Software applications are designed and developed with functionality first, and security is a distant second. We want to change that. A constant security vigilance is something you must have throughout the entire development life cycle in order to truly develop secure applications. And finally, we looked at a few standards, models, and frameworks that might help guide your thought processes in this area. You're going to see more of this in the subsequent modules.